All right, as we get started today, I want to go ahead and review over DeMoivre's theorem. Remember, DeMoivre laid out how to raise a trig form complex number to a power. Go and write this in your notes if you would. 2 times the cosine of 24 degrees plus I times the sine of 24 degrees. And let's raise that trig form complex number to the 5th power. Add your seats. We're going to work on that one, then I've got a couple more for you as well. By the way, if you're observing the number line and thinking, oh boy, I recognize that, we finally get an easy lesson, I'm sorry to disappoint you. That is up for the 7th graders coming in here later today. But somebody was lazy and didn't want to have to draw another number line. let's go ahead and take a look at these here. When I raise a trig form complex number to a power, the first thing I've got to do, Quentin, is
raise the r value to the nth power.
Good. Raise the r value to the nth power. I love how you said it. Perfectly mathematically good. And I get 32. The next thing I'll need to do, Jamie,
is multiply the 24 by the 5.
Good. Take the theta and multiply it by the n. So find the product of n and theta to get the cosine of
120.
There we go. And as always, we always convert back to standard form, right, Quentin? And so when we convert this back to the standard form, of course, we need to think, well, what reference angle do we have, class? In quadrant 2. And so cosine of 60, class?
-1/2.
Half. And then, of course, in quadrant 2, it is negative. And the sine of 60? And in quadrant 2. Of course, don't forget the I. And then we're going to take the 32 and distribute it through to wind up with what answer, Jamie?
-16 plus 69 times square root of 3.
And there we go. Good to go on that one? All right, looking at the next one, kind of talk me through this one now, Quentin.
Raise the 3 to the third power.
And cube it, right, to get?
27.
Then
Multiply the angle by 3. That's 225. Your reference angle.
that's a degree sign.
Your reference angle is 45. And quadrant 3. So square root of 2 negative square root of 2 over 2 minus I square root of 2 over 2 and distribute 27, so negative 27 square root of 2 over 2 minus 27 I square root of 2 over 2.
It's a pretty ugly answer, but it's correct. Good to go on that one. Looking at the next one, Jamie, here we've got a negative exponent. Negative exponent means reciprocal. So I'm going to take the reciprocal of this and cube the reciprocal. Well, what's the reciprocal?
2.
And if you cube the reciprocal, you get 8. All right. Good on that? All right. If you have questions, YouTube, let me know. Then we have to multiply theta by the n, but the n is a -3. Now, if you're treating it like a power, you actually take the reciprocal. But we're just straight up multiplying. We're not raising to the -3 power. Now we're just multiplying. So we literally get the cosine of
210, -210.
negative 210 degrees plus I times the sine of negative 210 degrees. Now we've got a couple options here with these negative 210s. One option would be,
Add 362.
that's probably the easiest option. Is that what you did as well? What's the other option though? With a negative angle.
Pull the negative for cosine, it goes away. And then
There was supposed to be a snap there. Okay.
for the sine, it moves to the front.
There we go. So we could add 360, in which case we would get 150. Or gone, and then move that to make it negative I sine 210. I think I like the 150 method. That way we don't end up losing this negative right here potentially. Of course, this negative would always go away. This negative would always move to the front, but I'd hate to lose that and somehow fail to account for it. So let's just go with the 150. I think that avoids mistakes, and that's a big part of math, right? Is finding ways to avoid mistakes. All right, from here, Jamie.
We take the cosine 150.
Well, kind of. We take the cosine of 150 by taking the cosine of its reference angle, 30, and recognizing that because it's in quadrant 2, that's going to affect the SIGN in each case.
So it'll be negative square root of 3 over 2 plus I sine of 1/2.
Well, not sine of a half, just a half. All right, and then of course we'll distribute the 8 to get
negative 4 times the square root of 3 plus 4i.
And there we go. And good to go on that one as well. All right, questions on DeMoivre's theorem as it relates to raising to powers. But in our last lesson, we began finding roots using DeMoivre's theorem. And the premise was this, that a square root can be written as a power. Remember, the square root is simply written as the what power? For instance, I could say the square root of 5, or I could say 5 to the 1/2 power. The 17th root of Jamie could be written as Jamie to the 1/17th. I don't know why you do that, but just, randomly popped into my head. Guess I'm in a weird mood today. Just today. Anyway, but yeah, so fractional exponents, remember, can be used to represent roots. So if I had the 4th root of 16, I could write that as 16, not times a 4th,
Yeah.
16 to the 1/4 power. But remember what we said in our last lesson is we're going to change that to 16 times 1, all to the 1/4 power. But we didn't write a 1. I wrote an expression in the trig form that equaled 1. Good. We would say 16 times the cosine of 0 degrees plus I times the sine of 0 degrees, all to the 1/4 power. Now, we should know this, going back in our minds to our algebra days. We memorized what the 4th root of 16 was, class? It's 2. But you also know there's 4 of them. The principal root is 2. And that's what we would end up with here. But to find the other 4, well, technically you could take successive square roots, that's true. But to practice using DeMoivre's theorem, we said this, we've got to do this again. But instead of using 0 degrees, we're going to use an alternate form of 0. That's not the same thing. 360. So we could then take 16 times the cosine of 360 degrees and raise all of that to the 1/4 power. I'm too lazy to write plus I sine 360, so that's what the dot 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 means. Then we could do the same thing again, but instead of 360, we could use 720, blah, blah, blah. And then we could do it a 4th time and use 1080 degrees. All of these over and over again raising to the power. Well, each time you do, remember, using DeMoivre's theorem, we're going to start by saying, well, 16 to the 1/4 power, the principal root is 2 every single time. But with the angle, remember, we actually have to multiply, just as we did a moment ago with the regular exponents. 0 times a 4th still gives me 0. Which is why, since this still all equals 1, we get that principal root 2 again. But when we multiply this times a 4th, I don't get 0. What do I get? 90. Well, that's not just going to be 2, that's going to be something else. When I multiply this times a 4th, I'm going to get a 4th of 720. 180. And by the way, do you notice the pattern? 0, 90, 180. Without even looking back here, what should the next angle be? 270. And remember in the last lesson I showed that the angles will always be symmetric about the complex plane. So here, cosine 90, what is the cosine of 90? 0. What's the sine of 90? 1. So 2 times 0, 2 times I times 1. There's another of my 4th roots. Well, we could have gotten that by successive square roots, right? What's the cosine of, well, 180 has what reference angle? 0. But it's in quadrant 2/3, right? Cosine of 0, 1. But in either quadrant 2 or 3, cosine is negative. Sine of 0 is 0i, so that kind of just drops off. 2 times -1, positive -2. And of course here, the reference angle is 90. So it's going to do the same thing as this, except because it's quadrant 3/4, it's going to be a -1. So I get positive -2i. Again, we could have taken successive square roots to get this particular answer, but that's not always the case, right? As we showed in the last lesson. So some things as by way of reminder, the symmetry here is going to help us to go a lot faster. We don't necessarily have to put a lot of work into the front end once we see the pattern from the first couple. For instance, let's go with a big ugly one here. Let's go with the fifth, well, no, let's go with an easy one, and then we'll do the ugly. Cube roots of 27. Cube roots of 27. Now, just by way of reminder, if, for some reason, you saw this, it's indicating it wants the principal cube root. But if you had x cubed equals 27, now you're putting that cube root in, now you have to take all three. Or if it said, what are the cube roots of 27? You know, but given this symbol, that implies principal root. If the symbol is presented to you, it assumes principal root. So, I'm going to start by rewriting the 27 as 27 times. I'm going to raise all of it. If I want the cube root, raise all of it to the 1/3 power. Doing it with me. But we're going to do it how many total times? 3. The first time, of course, we use 0 degrees. The next time?
360.
And the next time?
720.
Each time, we're going to lead off by taking the principal cube root of 27. 3. And then we're going to multiply angle times 1/3. Well, in this case, my angle is 0. The next time, the angle is going to be 120. Now here, I don't really have to take 1/3 of 720, do I? I see the pattern. 0, 120, what comes next? And if you want to check and make sure that you didn't screw up, like I just did, on your angle, do another 120 and it better hit 360. It has to end, it would have to hit 360 if you went one more, and it does. All right, so again, is this a long process? No. What I showed in our last lesson seemed like forever long, but there's ways in which you can make this really quick and easy. Because I already know my first answer is always just going to be the principal root, in this case 3, right? Because this is always just 1. In this case, my reference angle, quadrant, sine of 60, or cosine of 60, 1/2, and in quadrant 2, sine of 60, in quadrant 2, don't lose the I, we distribute, and you're doing this with me on your paper.
3 over 2 plus 3i squared 3 over 2.
It ain't pretty, but it's correct. That's one of the cube roots of 27 we didn't used to find. Now for the next one, reference angle. Oh, well, we already know those values. I'm not going to recalculate them, but it's quadrant 3. So this is still negative. Now this is negative. Now we distribute to get this again, but with both of them negatives now. Does that make sense? If it's the same reference angle, the answer is going to look the exact same, except you're going to account for a quadrant 3 where they're both negative. And boom, there's my 3 cube roots of 27, and it didn't take that long. Now, if I had something a little more annoying, for instance, I wanted to take the fifth, or find rather, the fifth roots of 32. Again, start by writing 32 times and raising it all to the 1/5 power. Then the next time we're going to do it again, but instead of 0, we're going to use, and the next time, and the next time something else, and the next time something else, right? Because we're too lazy to figure those out. All right, then each time, we're going to take the principal fifth root of 32 that we memorized. 2. And then each time, we're going to actually take a fifth of the angle. So a fifth of 0 gives me. So I'm going to put cosine 0 plus I sine 0. Then we're going to take a fifth of 360.
72.
72. Cosine 72 plus I sine 72. Then we're going to take a fifth of 720.
144.
Cosine 144 plus I sine 144. What's the pattern?
72. That's 72.
All right, so what's the next angle?
260.
216 plus I sine 216. So what's the next angle got to be?
288.
288. How do I make sure I'm on the right track here?
The next one should be 360.
Add 72 more and make sure it hits 360. Does it?
Mm-hmm.
All right, then we're good. Here's the problem. None of these are special angles. Well, if they're not special angles, we get to pull up calculator. Now, we already know the first one, because cosine 0 plus I sine 0 is just a fancy way of saying 1. So this just equals 2. But the next one we're going to have to distribute. 2 times the cosine of 72. Let's go 2 decimal places.
0.62.
0.62. 2 times the sine of 72.
1.9.
2 decimal
Oh,
places.
1.90.
1.90. Don't forget the I. And that's my approximate. I guess technically we should say approximately equal to. Then, let's do the next one. 2 times cosine 144. What do we got?
Negative 1.62.
Negative 1.62? All right. What are the next one's going to be? Negative 0.90. Anyway, let's try 2 times the sine of 144.
1.18.
1.18. And notice it is positive because we're still in the second quadrant. Don't forget to put the I. All right, now let's do the 216.
Negative 1.62.
Ah, now do you realize that means these two share a reference angle? So I don't even need to recalculate the next one. Negative 1.62, quadrant 3, cosine's negative. Sine's going to be negative this time. Negative 1.18 I. Do you see we're still recognizing patterns? All right, 2 times cosine 288.
0.62.
Oh, look at that. It's repeating this one now. So 0.62, but notice we're in the fourth quadrant, so I'm going to put minus 1.90 I. And there are my 5 fifth roots of 32. Again, back in algebra class, I told you they were there. You just couldn't find them yet. You needed trig. We've got trig. We've got all the roots we've been missing all these years. All right? Questions on this? Feeling comfortable with pattern? Feeling like, no, actually, this is not actually that scary. It's, now, admittedly, maybe a little annoying with all the calculator work, right? But as far as getting the trig form answers, at least, that's a piece of cake. That's a breeze, right? Now let's go big here. Let's go sixth roots. Let's do sixth roots of 1. Remember, it has as many roots as we want it to have. Let's find all 6 sixth roots of 1. Now you probably can already guess what 2 of them are. Positive, negative 1, right? We know those are going to be there for us. It's just, what are the other 4? All right, so we start with 1 times,
Or cosine 0 plus I sine 0.
and we're going to raise all of it to the
1/6
power. My next angle is going to be
360.
then,
720.
and then 3 more angles. Usually I'll do the first few just to make sure I'm on the right track, and then from there I'll just, yeah, there's going to be more stuff. Every time we find a root, we're going to start by raising 1 to the 1/6 power, the principal 6th root of 1, which is 1. Then we're going to multiply the angle by a 6th. So the first time we do it, of course, the 6th of 0 is
Yeah.
0. Because the first root you find will always be the principal root. The next time you're going to take a sixth of 360.
60.
Now, the pattern is 60. But I like to get a third one just to make sure I didn't mess something up here. So a sixth of 720
120.
is the pattern holding consistent. Again, it ought to. If not, there's something somewhere you made a mistake. But just, okay, so we're comfortable with 60, right? So what's the next angle? 180, so cosine 180 plus I sine 180. And the next one? Cosine 240 plus I sine 240. And then the last one?
300.
Cosine 300 plus I sine 300. How can I check and make sure I'm on the right track still? If you added 60 more, you get 360, and yes, that holds true. All right, cosine 60. Sine of 60. And of course, don't lose the I, and we're distributing a 1, right? Is there really any? It's just a half plus I squared of 3 over 2. 120, what's the reference angle? Oh, wait, you mean the same thing I just had? But we're in quadrant 2, where cosine is negative, sine is positive. 180, what's the reference angle? 0, but it's the opposite of 0. So instead of 1, negative 1. We already knew about that one, right? 240, what's the reference angle? Oh, you mean like those 60s, but it's in quadrant 3 where they're both negative. So negative a half, negative I squared of 3 over 2. All right, 300 reference angle. Oh, so what's the answer?
1/2 minus I squared 3 over 2.
Positive a half minus I squared 3 over 2. And those are the sixth roots of 1. Easy enough. I mean, it is repeatable. Now, again, something like a 7th root would be really obnoxious because 360 doesn't divide by 7. So 7th roots are going to come out really weird, okay? You know, cosine of 367ths, sine of 367ths, 727ths, you know, it would be, you know, it's going to be obnoxious working with that. But any root, any value, it's just really nice when their numbers, at least the principal root comes out evenly, is at least nice. I mean, I suppose, heaven help us, we took the 5th roots, we just did a 5th. Well, anyway, let's do the 5th roots of 5. Well, then in that case, when we do 5 and then we raise into the 1/5 power, I'd have a 5th root of 5, 5th root of 5, 5th root of 5. And that's going to be really annoying, but it's still doable. It's just obnoxious. Okay? Write this equation now on your paper, because again, the point of this was, as we solve equations, getting all the answers, as opposed to, like I said before, what we had to do in Algebra 1 and Algebra 2, where I said, well, I know there's more answers. I just don't know what they are. Write this equation down, if you would. X cubed minus 12 equals 113. We know in a cubic equation we have to have 3 answers. So let's find them. Start by, to get x cubed equals,
120,
and then take the cube roots to get 3 answers at your seats. Find the 3 cube roots of 125 so that we have our answers. Jamie's got her 3 answers. Quentin's got his 3. All right, so starting off with 125 cosine 0 plus I sine 0 to the 1/3. We got a 360, we got a 720. That's going to be a 125. Again, that's going to be cosine 0 plus I sine 0. Excuse me, a 5 could be raised to the 1/3. We multiply by a third. We're going to have 120. We're going to have 240. Of course, that's just going to come out to 5 times 1, which is 5. 120 is going to be reference angle 60, quadrant 2. So my cosine 60, negative half, positive square root of 3 over 2 with the I. We distribute a 5, so negative 5 halves plus 5i squared of 3 over 2. And we're going to do the same thing because the next is reference angle 60, but they're in quadrant 3 now, so both should be negative. So negative 5 halves, negative 5i squared of 3 over 2. And that's like bare minimum work shown. Good to go on that? All right, write this one down. X to the 6th equals 65x cubed minus 64. I'm actually not sure if there is a name for a 6th power equation. There probably is some cool name, I just don't know what it is, and frankly don't care enough to look it up. But we got the 6th power equation, which means I should have 6 answers. Now the difference here is it's not what we would call incomplete form, where we isolate the 6th power, take the 6th root. It's in a complete quadratic look, where I need to set it equal to 0. So walk me through that, Jamie.
We'll move this stuff on the right side to the left, so it's x to the 6th power minus 65, x cubed plus 64 equals 0.
And then, Quentin, and then I'm going to take each of those factors, set them both to 0 to get a couple little mini equations here, Jamie.
You'll have x cubed equals 64 and x cubed equals 1.
All right, I would have put them in the opposite order, but you might have put the 64 in 1 instead of 1 in 64. But it's okay, same 2 equations. And now I've got to take a couple of cube roots. So that's your seeds. We know there's going to be 6 answers. 3 here, 3 here. Give me all 6 answers for x. what were your 6 cube roots in 2 sets here, Jamie?
4, negative 2 plus 2i times the square root of 3, negative 2 minus 2i times the square root of 3, 1, negative 1/2 plus I times the square root of 3 all over 2, and negative 1/2 negative I times the square root of 3 all over 2.
Good to go. There we go. So equations like this that we worked, and before we said x equals 4, x equals 1, and there's 4 more answers that are complex. Like we literally worked this problem earlier this year in Algebra 2, not you guys, but my Algebra 2 class. You guys can finish the problem. All right, questions on this? All right, your homework for this evening is to complete a handout as we wrap up Chapter 9 and wrapping up trigonometry. We'll be moving into the second half of the course, Analytic Geometry, on our next lesson. But for homework this evening, have a handout for you. If you're watching on YouTube, it is in the description of the video. So wrapping up with a quiz in our next lesson. We'll go over the handout, of course, first, as that'll give you a good review for the quiz, and then transitioning into Chapter 10. All right, have a wonderful rest of your day.